Example 8. Suppose an investment is growing by 7% each year. How long does it take the investment to double in value? In this example, the investment depends on time, so the investment is a function of time. Notice it's growing at a constant percentage rate of 7% each year. That means this is an exponential function. The form of the formula for an exponential function is amount after t periods equals initial value times 1 plus r to the t, where r is the percent increase each period. In this example, a period refers to a year, and r is 7% or 0.07 as a decimal. With this said, our formula becomes amount after t years equals initial value times 1 plus 0.07 to the t power. We are not given the initial value, yet we want to know how long it will take for the initial value to double in value. This means the amount we're interested in is 2 times whatever the initial value is. When we put that into our formula, we get 2 times initial value equals initial value times 1 plus 0.07 to the t power. When solving an equation, we like to have only one unknown. And at this point, we have 2 unknowns. We don't know the initial value, and we don't know t. But since initial value is being multiplied on both sides of the equation, we can simply divide the entire equation by initial value and get rid of that unknown. Notice, since division undoes multiplication, initial value cancels out on the left side of the equation and the right side of the equation. The result is 2 equals 1.07 to the t power. Now we have one equation and one unknown. This seems more manageable. Also, notice it doesn't seem to matter what the initial value was, which is probably why it wasn't given to us in the problem. Our equation now is in the same form it was in example 7 when we had 1.6 equals 1.005 to the t power. Recall that it was difficult to solve for t because t was trapped in the exponent. So instead, we took the log of both sides of the equation, and then we used the property of logarithms to bring the t outside of the logarithm as a factor in a multiplication problem. Let's do the same thing here. When we take the log of both sides of the equation, we get log 2 equals log 1.07 to the t power. Now we'll use the property of logarithms to bring the t outside of the logarithm and multiply it by the log of 1.07. Even though this looks complicated, this is just a number equals t times another number. This equation is really in the same form of the equation 10 equals 5 times t. To solve 10 equals 5 times t, we would simply divide both sides by 5. To solve log of 2 equals t times log of 1.07, we will divide both sides by log of 1.07. When we do this, log of 1.07 cancels out on the right, and we get t equals log of 2 divided by log of 1.07. When we put this in our calculator, we get log of 2 divided by log of 1.07 is approximately 10.2. If you're not getting this answer, try entering log of 2 divided by log of 1.07 again into your calculator, and this time be very careful with the parentheses. You want to make sure there's parentheses surrounding 2 and parentheses surrounding 1.07. Also, you shouldn't get exactly 10.2 as your answer, but you should get 10.2 when you round to one decimal place. Finally, we need to label our answer. Since t is our independent variable, and our independent variable is in years, 10.2 is the number of years it will take for our investment to double. Example 9. Suppose the charcoal from an ancient campfire is found to contain only 1/3 of the carbon-14 of a living tree. How long ago did the tree that was the source of the charcoal die? Note, the half-life for carbon-14 is 5,770 years. In this example, the amount of carbon-14 found in the charcoal is the dependent variable, while time is the independent variable. Recall, the percentage decrease each half-life is 50% or 0.5. Since there's a constant percentage decrease, this is an example of exponential decay. And the form for the formula for exponential decay is as follows. Amount after t periods equals initial value times 1 minus r to the t, where r is the percentage decrease each period. Since in this example we are working with half-lives, we will use the variable h instead of t, and substitute 50% or 0.5 in for r. We get amount after h half-lives equals initial value times 1 minus 0.5 to the h. Here the initial value is the amount of carbon-14 in the tree when the tree died. We don't know that amount, but it might not matter since we didn't know the initial value in example 8 and we were still able to solve for t. We are interested in finding out how long ago the tree that was the source of the charcoal died. In other words, how long did it take for the tree to lose all but 1/3 of the carbon-14 it contained when it died? That is, what is h when the amount of carbon-14 is 1/3 of the initial value? When I substitute 1/3 of initial value in for the amount, I get the following equation. Notice this looks pretty similar to the equation I began with in example 8, where I had 2 times the initial value equals initial value times 1 plus 0.07 to the t. And notice the very next step was dividing both sides by initial value, which resulted in an equation with just one unknown. Let's do the same thing with our equation in example 9. If I divide both sides by initial value, I get 1/3 equals 0.5 to the h power. In order to isolate h, we need h to no longer be an exponent. We might remember that the property of logarithms on the previous page undoes exponents. But in order to use the property of logarithms, we need the right side of this equation to be of the form log of something to the h power. Remember, when working with equations, we could perform whatever operation we would like as long as we do the same thing to both sides. Let's take the log of both sides so that we have log of 0.5 to the h, the form needed to use the property of logarithms. We get log of 1/3 equals log of 0.5 to the h power. After using the property of logarithms, the right side becomes h times log of 0.5. Note that h is no longer trapped as an exponent. This might look complicated, but remember, log of 1/3 and log of 0.5 are just numbers. So this is an equation of the form number equals h times a number. We can isolate h by dividing both sides by log of 0.5. When we do that, the log of 0.5s on the right cancel out, and we're left with h equals log of 1/3 divided by log of 0.5, which according to my calculator is approximately 1.58 half-lives. We use the variable h instead of t to remind us that the unit for the independent variable is half-lives. With that said, 1.58 half-lives doesn't do a great job of answering the original question of how long ago did the tree that was the source of the charcoal die. Since most people don't know how long a half-life of carbon-14 is, we should probably convert our answer to a more recognizable unit. We have that the half-life for carbon-14 is 5,770 years. This means 1.58 half-lives is 1.58 times 5,770, or 9,116.6 years. Thus, the tree that was the source of the charcoal died almost 9,117 years ago. Summary: when measuring an earthquake, an increase of 1 unit on the Richter scale corresponds to increasing the relative intensity by a factor of 10. An increase of t units in magnitude corresponds to increasing the relative intensity by a factor of 10 to the t. When measuring sound, an increase of 1 decibel multiplies relative intensity by approximately 1.26, while an increase of t decibels multiplies relative intensity by approximately 1.26 to the t power. Finally, suppose a quantity grows as an exponential function with a given base. To find the time t required to multiply the initial value by k, we use logarithms to solve the equation k times initial value equals initial value times base to the t. The solution is t equals log of k divided by log of the base.